our speaker for the evening, Mia de los Reyes from Caltech, and she is going to be speaking to us about the loneliest galaxies in the universe. And so with that, Mia.
Hi everyone, it's so good to be here. Give me a few seconds to set up my screen share and then we'll get started.
Okay, I can blab while she's talking. Let's see. Oh, back on the test slide that I wanted to just remind everyone that our organization has a whole group where we check the candidates from NASA's test satellite and we verify them as actual exoplanets for NASA. And so our organization has a whole activity where they send us candidates. We observe them with the long time frames that we can provide, and then we send them back our data in the format that they request. And so if you're interested in doing that kind of thing, I would encourage you to attend next week's meeting, which is run by Scott Dixon, who heads that effort with Pat Boyce, who I think is also here this evening. And so with that, I can see Mia appears to be ready, so I'll turn it back over to Mia.
All right, hi everyone. Thanks so much for spending your Wednesday night here listening to me chat about the loneliest galaxies in the universe. So just introduce myself. My name is Mia de los Reyes. I'm a grad student at Caltech, so I'm doing my PhD there. And yeah, I don't like talking for extremely long periods of time, so I'll take breaks and ask for questions. So feel free to drop questions in the chat, or when I pause, I'll pause maybe 2 or 3 times. Feel free to unmute and ask questions then. All right, so before I get started talking about galaxies, I just want to take a quick moment to acknowledge where the data come from. So many of you are astrophotographers. You understand that a lot of the journey is just taking the data and like getting beautiful images and other observations of objects in space. And so I think it's really important to acknowledge where this comes from, especially because the data in this that I'll talk about are from the Keck telescope, which is located on the mountain of Mauna Kea in Hawaii, which is a really important cultural role. So to many of the Native Hawaiians or the Kanaka Maoli, Mauna Kea is sacred, or is very significant. And so I think it's really important to acknowledge that every time we talk about the science that we get from these observations. All right, so today I'm going to be talking about galaxies. So let's start with what exactly is a galaxy. Here's a really nice picture of a face-on galaxy, and we can see that it's made up of stars. That's giving off most of the light of the galaxy. There's also gas and dust, as we saw in some of those beautiful photos that folks took earlier. There's a lot of gas and dust in between the stars. And then finally, something that's not in this picture of a galaxy, but is a really important component, is dark matter. And galaxies are actually often defined by how much dark matter they have. But unfortunately, we don't know what it is, and I won't be talking about it very much in this talk, because at heart, I'm an observer. I like to use data that we can see, and we haven't been able to figure out what dark matter is, and it's very difficult to observe directly. So I won't talk too much about it. All right, the galaxies, they come in a huge range of shapes and sizes. I think when people typically think of galaxies, the first image that comes to mind might be something like our own Milky Way, or maybe our neighbor, the Andromeda Galaxy. So here on the left is a really nice time lapse that I think is just very cool, because most astrophotography time lapses tend to show the sky moving over the Earth. But then this one, the Milky Way in the background is fixed. You can see here, while the Earth is rotating. So you can actually see the rotation of the Earth through space. So I just think that's really cool. I kind of just wanted an excuse to stick this in here. But the Milky Way, from our vantage point, it looks a bit like this, band of a way of milk that stretches across the sky. But from an outsider's perspective, it would look a little more like the Andromeda Galaxy, which is our nearest massive galactic neighbor. So the Andromeda Galaxy, or M31, is also sometimes visible as sort of a fuzzy patch, even with the naked eye on a nice clear night. And maybe I'm dating myself, but also when I was an undergrad, it was also the default background for the Mac OS. So maybe this picture is familiar to you. So both the Milky Way and Andromeda are sort of typical spiral galaxies. They have these really beautiful spiral arms. This is an artist's impression of what the Milky Way would look like if we could see it from outside of it. But there are a lot of other kinds of galaxies too. There's also elliptical galaxies. So here on the right, Elliptical galaxies are just giant ellipses, elliptical blobs of stars, and they don't have the beautiful spiral structure. And then on the left, we have irregular galaxies, which are neither spiral nor elliptical, they're just irregular. And so one of the big questions in galaxy evolution is actually, how do we get this huge variety of different shapes, of different galaxy morphologies? And we think that one of the keys actually has to do with galaxy interactions. So here's a nice video that I think shows this really well. So this was done by folks at the Space Telescope Science Institute. So it'll show a simulation of two spiral galaxies that are going to merge together. And throughout the video, they'll actually pause it, like here, and overlay real images that have been taken mostly with the Hubble Space Telescope. So images of real galaxies. So you can see how a lot of the images that we take of galaxies are actually just different vantage points of sort of the same kind of system. And so you can see these two spiral galaxies are beginning to merge. And as they continue to interact, the spiral structure actually begins to get disrupted. And so these galaxies begin throwing out these really beautiful, what we call tidal tails, these streams of stars that are caused by the gravitational interactions and tidal interactions between the two systems. And so we lose the initial spiral structures. They both started out like spiral galaxies like the Milky Way, but over time, as they throw out these tails, eventually all that's going to be left behind is this inner core, which will actually merge and form an elliptical galaxy. And so this sort of shows how you can get from one morphology of galaxy, from spiral galaxies to elliptical galaxies through interactions. And so interactions we think are really important for galaxy evolution. And we'll come back to that a little more later, and we'll talk about that more in detail, about how that might work. But all right, so there's the credits, which are important. But importantly, you know, these galaxy interactions, like galaxy mergers, are not the only piece of the puzzle. There's still a lot of open questions about galaxy morphologies. So we've showed, for instance, how to get from spiral galaxies to elliptical galaxies. But maybe there's a way to go the other way, to get a spiral galaxy from an elliptical galaxy. And actually, it's a big open question how we get these spiral arms in the first place, and what the very first galaxies look like. And if you're interested in helping answer these questions, actually, a really good way to do this is through one of my favorite websites, galaxyzoo.org. So it's actually a citizen science project. It turns out we have tons of data, tons of images of different galaxies, but we have a lot of trouble classifying them because computers are actually not very good at looking at images and classifying them, right? This is the whole point between, like, every time if you forget your password and you have to do the CAPTCHA thing where you select all the streetlights or whatever. Because robots are not good, computers are not good at identifying and classifying images, but humans can do this really easily. And so if you have a few minutes out of your day, if you have kids at home and want to give them something to do, you might want to check out this website, which will allow you to help classify these galaxies so that scientists can actually use these data sets to answer these questions about how to get a huge range of galaxy shapes. All right, so far we've been talking about galaxy shapes, but galaxies also come in a huge range of different sizes. So the Milky Way and Andromeda are, we'll call those sort of Milky Way mass. They're sort of the most common massive galaxies in the universe. But we also get galaxies that are much less massive, these low mass galaxies that we call dwarf galaxies. And we get a couple of galaxies that are much more massive than the Milky Way. And to put some numbers on these different categories, a Milky Way-like galaxy will have roughly 100 billion stars, whereas massive galaxies have trillions of stars, and dwarf galaxies have on the order of millions to billions of stars. So that's a pretty huge range. And I realize that all these numbers, humans are not very good at really understanding what numbers this big are. Like, we don't have that sense of scale. And so to put this on maybe an easier to understand scale, instead of talking about numbers of stars, we're going to convert this to numbers of people. So 100 billion stars, we'll say that's roughly equivalent to 100,000 people. And on this scale, the Milky Way is around the size of sort of a mid-sized city like Pasadena, which is where Caltech is located, or Raleigh, North Carolina, which is actually, that's where I am right now. I actually left California to be with my family during this deeply weird 2020 year. And so they live in Raleigh. So a mid-sized city is sort of the Milky Way and on this scale. And then on this scale, San Diego would actually be sort of one of these extremely massive galaxies with millions of people. So San Diego, LA, New York, those are really like the biggest galaxies. And then dwarf galaxies are, again, they cover a pretty wide range of galaxy masses. So on this scale, they could be anything from a group of thousands of people, so something like Caltech, like a university, which has a small university with thousands of people, like down to just one person, so like me. And so in this talk, we're mostly going to be focusing on dwarf galaxies. All right, so now you might be wondering, why study these dwarf galaxies? Why not study like the biggest and, or the ones like the Milky Way, because they're the most like our home. But for me, dwarf galaxies are really interesting for a couple of different reasons. So in the same way that, families or individuals are way more common than cities, there are also way more dwarf galaxies than there are Milky Way mass galaxies. So for context, the Milky Way and Andromeda are the two sort of big galaxies in what we call the local group, like our local neighborhood of galaxies. So there are only two of these big galaxies, but there are on the order of 40 of these tiny dwarf galaxies. And so that makes them really easy to study. They're close by, there's a ton of them. They all have different properties, so you can study them pretty well. And so that for me is one of the sort of convenience is one of the reasons to study these dwarf galaxies. They're also pretty simple. So in the same way that, a single person or maybe a family, the way that the members of a family might interact are, there aren't that many interactions. It's relatively easy to follow compared to a city. If you tried to follow every single person in a city, that's much, much harder to do. So in the exact same way, dwarf galaxies are relatively simple compared to Milky Way-like galaxies. So the Milky Way has, it has a disk, it has a bulge, it has a halo of stars around, it has all these different components. But a lot of dwarf galaxies are really just blobs of stars and gas. So they're much easier to understand and to model. And then finally, as Steve mentioned earlier, there's also sort of the aesthetic reason to be interested in astronomy. And I actually just think dwarf galaxies are really cute. So this is my favorite dwarf galaxy sculpture, and I have given it a face to properly convey how I feel about it. All right. So to recap so far, low mass dwarf galaxies are interesting. That's really the key takeaway of this first part of the talk. And now I'll take a break and see, it looks like we have a couple of questions on the chat. Let me see. Yeah, I can try to answer some of them. All right, so we have a couple questions. Why do some galaxies have arms? That's actually a great question. It's an open question. It's something that we're still trying to understand. Roughly what we think spiral arms are here, let me go actually find a picture of spiral arms to help illustrate this a little better. So we think that when you get a mass of, there we go. If you have a mass, like a gas cloud or whatever, and it begins to rotate, like if you have a big ball of pizza dough, for instance, and you rotate it, it'll flatten out into a disk through conservation of angular momentum. And so I think this is a really nice way of, like the pizza dough image, I think if you just toss it a little bit, you get a flat, thin disk. And so that's where the disk comes from. And we think the spiral arms build up because we get these waves in the disk. So it's not really waves of stars, it's more like waves of, they're called density waves. It's kind of the same as in a traffic jam. The traffic jam sort of stays in the same place, even though the cars moving through it are always different, right? You slow down and then you leave the traffic jam, but the traffic jam is still there. And that's basically what a density wave is. It's kind of like a traffic jam, but for stars. And so we think that's what spiral arms are, and how they form is still very much an open question. So that's a great question. And then Mike had a question, how is a galaxy defined versus a cluster? So that's a really great point. This is something that's actually starting to get a little, this has had a long and sort of contentious history among some astronomers. So historically, we define galaxies as systems that are above a certain mass. So again, dwarf galaxies, the cutoff is usually around millions of stars. And then clusters tend to have fewer than that, so on the order of tens of thousands or hundreds of thousands of stars. The other big difference between these two systems, galaxies have more dark matter. And so the idea is that a galaxy is something that has enough dark matter that it can actually hold on to the products. So I'll get to this a little later. But as stars live and die, they create heavy elements. And when they die, they can sometimes also, they go supernova, they inject energy into the galaxy, and that can actually throw out some of the heavy elements unless the galaxy is massive enough that its gravitational its gravitational potential is strong enough to keep those metals in there. And so you need a lot of dark matter in order to be that massive. And so sometimes that's how people define what a galaxy is. So it's getting a little fuzzy again, especially recently, because folks have started discovering galaxies that don't appear to have a lot of dark matter. And so now we're sort of opening this can of worms about what exactly is a galaxy all over again. And then we have a couple more questions from Alec and Joel. I think we'll have to save some of these for the end, maybe, just so I can get through this presentation in time. Yeah, Joel is asking, do dwarf galaxies usually form on their own, or are they also the result of galaxy interactions? That's actually a great question. That will be answered later in the talk, or hopefully we'll answer it later in the talk. And if not, I'll try to address it again at the end. And then there was a question from Alec. I think I'll also save that one for the end, if that's okay. All right, thanks so much for these questions. They're really, really great. I love answering questions and I'm super happy to do so. Okay, let's head back to the actual talk. Where was I? Okay, so we were here. Low mass dwarf galaxies are really interesting. All right, so now we're going to zoom out a little bit. Instead of talking about individual galaxies, we're going to zoom out and look at the big picture of the universe as a whole, not just individual galaxies, but sort of the large scale structure. And on the large scale, we can describe our universe with a cosmological model called Lambda CDM. This is a lot of words that we don't typically use in our day-to-day life, so I'll break this down a little bit. So here, cosmological just means referring to sort of the big picture, the large scale structure and evolution of the universe. So the shape of the universe, how it's expanding, if it's contracting, how the large scale structures form. And we have a cosmological model that we think describes the universe pretty well, and it's called Lambda CDM, where lambda is what we call a cosmological constant. So we can tell from observations that the universe is expanding and that its expansion is getting faster and faster, it's accelerating. And we don't know what's driving it, but we do know that mathematically you can describe this pretty well by inserting a constant into some equations. And so we call that constant the cosmological constant. Another name for it is dark energy. And so we think that this model of dark energy seems to match observations pretty well. And then the other part of the Lambda CDM model is the CDM part, which just stands for cold dark matter, where dark matter is just matter that we can't see. We know it's there because it's interacting gravitationally with other matter that we can see. And it's cold in the sense that it's not moving very fast relative to light. So it's not moving what we call relativistically. And so Lambda CDM put together we think it describes a lot of the large scale observations that we've made about the universe. But it also makes predictions about sort of how structures form overall in the universe. And we can actually figure out what those predictions are by looking at simulations. So here's an example from the Illustrious simulation, which is a pretty large collaboration. And basically what they do is they build a model based on Lambda CDM, and then they put all of the physics that they can think of into a supercomputer. So that includes, how gravity works, and to some extent how light works, how electromagnetism works. They put all of this in and they're able to simulate what the universe looks like, in a box, basically. It's really cool. And so here's a snapshot of one of those simulations. And on the left side, the blue part, that's showing the density of dark matter. So in the bright spots, there's a lot of dark matter, and in the darker spots, there's not as much dark matter. And on the right side, they're doing the same thing, except this time they're coloring it by gas density. So again, the bright spots have a lot of gas, the dark spots have not as much gas. And if you were to overlay those things on top of each other, the blue and the orange, they would actually overlap fairly well. And that's because both dark matter and gas, they follow each other, and they're gravitationally attracted to each other. So both dark matter and visible matter tend to follow each other in the universe. And we can see that we see this like filamentary structure, right? We see these bright nodes where there's a lot of matter, a lot of dark matter and a lot of gas, and these sort of long filaments connecting it with other nodes. And you might be wondering, like, maybe that's just a weird simulation thing, maybe they did something wrong. But we can actually check that with observations, and that's what people do. So here's an example from a galaxy survey, where the goal was basically to map as many galaxies in the sky as possible. So here is a snapshot of that map. Here's the Milky Way right at the center. And it's sort of the same as looking up at the sky, and the farther away you get from the center, the farther away from Earth you're looking. And this is just in different directions. And you can see the same filamentary structure. So at every single dot, they just put a dot everywhere there was a galaxy. And so the bright orange parts, there's a lot of galaxies, and then the parts where there are no dots at all, there's not many galaxies. And we see the same sort of long stringy filaments connecting the different parts of the sky. And we call this filamentary structure the cosmic web because it looks like a web. It looks kind of like a spider web. We're not incredibly creative at naming things. And the cosmic web is sort of one of the biggest predictions of Lambda CDM, this pattern that we see in both simulations and observations. So Lambda CDM also makes some predictions about the small scale structure of the universe, so how individual galaxies form. In particular, it predicts that galaxies get built up from smaller and smaller bits over time. So here are more snapshots from this illustrious simulation going through time from left to right. So at early times, you can see the bright spots where the galaxies live are not very big. But over time, they grow bigger and bigger. They sort of build up from all of these small nodes. They sort of glom together and make bigger ones. And we can maybe see that a little better if we trace a single galaxy over time. So here's a nice cartoon that I think shows this really well. So now time is going from top to bottom. And so in the early universe, at early times, we have all these small galaxies. And then over time, those small galaxies merge, they interact and produce bigger galaxies. And then those galaxies merge, and you get bigger galaxies, and so on until we have these big, massive structures like the Milky Way, a little more, and the more recent universe. And so again, this comes back to the idea that galaxy interactions are really important. So as we can see here, galaxies actually evolve by merging. And so what that tells us is that galaxy environments must be really important. Because if you can think of, if you're a galaxy and there's a lot of stuff in your environment, a lot of other galaxies near you, you're going to evolve faster because you're more likely to interact with them more frequently. On the other end, and sort of the other extreme, is if you're in a super low density environment, if there aren't really any galaxies around you. So here's an example, going back to this picture of the cosmic web. These low density environments are what we call cosmic voids. So again, here we see the filaments of the cosmic web, but in between these filaments where all the galaxies live, there are also these voids. And those cosmic voids are not actually empty. They're super low density, but there are actually galaxies there. And so by studying the galaxies in these environments, we can actually learn a lot about how galaxies evolve at sort of the extreme, in really extreme environments when they're completely isolated. And in particular, I spent a lot of the first part of the talk sort of talking about how dwarf galaxies are really interesting. But now I'm going to talk about why dwarf galaxies in cosmic voids are particularly interesting. So for one reason is because they might be really similar to galaxies in the early universe. So again, going back to this picture of how galaxies evolve over time, the galaxies in the early universe are these small galaxies that haven't had time to interact very much. And that's exactly what a dwarf galaxy in a cosmic void is. It's a small galaxy and it's in a void, so it also hasn't been able to interact very much. And so by studying dwarf galaxies in cosmic voids, we can actually understand what the earliest galaxies in the universe might be like. So I think that's pretty interesting. It's like a time machine. So instead of having to look all the way back to see these really, really faint galaxies, we can just look in these nearby cosmic voids to see galaxies that are pretty similar. Another reason is that because again, dwarf galaxies are sort of probing an extreme kind of environment, or dwarf galaxies in cosmic voids are in an extreme environment. This can tell us about how galaxy evolution works as a function of environment. So here's an example, a little closer to home. If we look at the Milky Way, and we look at two of the dwarf galaxies near the Milky Way. One of them, my favorite, Sculptor, is a dwarf spheroidal galaxy, which is actually gravitationally bound to the Milky Way. So it's pretty close to the Milky Way. And the other, the Cetus dwarf regular galaxy, is farther away, so it's not gravitationally bound. And you can already see that just by looking at these two pictures, you can see there are a couple of differences. The Sculptor kind of just looks like a blob of stars, but Cetus has like the gas and the dust that we're used to seeing that we saw in, you know, some of those beautiful images that folks showed earlier. And the difference is actually the main difference, the reason that they look so different is actually just because of how the difference in their distance from the Milky Way. So Cetus, which is farther away from the Milky Way, has a lot of gas, and so it's able to make stars, and it has the, you know, weird looking irregular structure. But Sculptor, it doesn't actually have gas because it's close enough to the Milky Way that the Milky Way has actually tidally stripped it. It's taken away its gas. And so Sculptor can't make any stars. And so the main difference between these two galaxies actually just has to do with how far away they are from the one galaxy. And so the dwarf galaxies and cosmic voids are an even more extreme test of how this might work, right? Because they're far away, not just from the Milky Way, but from every other galaxy. And so it's like if we have these two test cases, and then we took a test case way far away, like way off the left side of the screen. That's what the void dwarf galaxies are testing. And then finally, because these galaxies are almost completely isolated, they can tell us a lot about how galaxies grow on their own. Because a lot of the galaxies that we observe are interacting in some way, especially the dwarf galaxies. They're interacting with the more massive galaxies nearby. And so it's really difficult to untangle the effects of what's happening to the galaxy just on its own versus what's happening because it's interacting. And so by looking at these really isolated galaxies, we can really just nail down what's happening when galaxies are really on their own. All right, so just to recap again, low mass dwarf galaxies. In the first part, we talked about how these dwarf galaxies are really interesting. And in this section, I hope I've convinced you that dwarf galaxies in cosmic voids are especially interesting because they can be used to learn about galaxy evolution. All right, so I'm going to pause here again for some water and some questions. Let's see. We have a couple questions about dark matter and energy. And yes, Anton is right. The dark matter does not seem to be made of the same kind of matter that what we think of as chemicals are. So that's a good point. And then Peter brings up this point, how do galaxies merge to form pinwheels? So wouldn't the merged galaxy be more irregular? Yes, that's mostly true. One of the thoughts is that if you can turn an elliptical galaxy into a disk, and some simulations have shown that that's possible, not the most massive elliptical galaxies. This is pretty recent work, and it's very much an open question. Most of what I'm talking about, most things in galaxy evolution are open questions because galaxies are really complex systems. But we actually think there are some indications that you can turn an elliptical galaxy into a disk. And then once you have the disk, you can make the spiral arms. Maybe. Again, where the spiral arms come from is still unclear. And this is something that a lot of folks have a lot of opinions about. All right, so I think those are most of the questions from this section.
Mia?
Yeah.
Has there been a dwarf galaxy found recently that appears to have no dark matter?
Yes, yeah, there have actually been a number of dwarf galaxies from the Dragonfly team, which so really quickly, I want to talk about the Dragonfly team because I think what they do is very cool. So they took a bunch of, they didn't have to, order actual astronomical instrumentation, which is, most of the telescopes that we think of for professional astronomy have to be, made in special labs, or like James Webb, they have to be made in a lab and then shipped a bunch of places or built on a mountain. But the Dragonfly team literally just bought, I think, a bunch of Canon cameras and basically put them all together, sort of in the same way that a dragonfly has like a compound eye. They took a bunch of these, the kind of camera you can buy at Best Buy, and they put them all together in sort of a compound structure and made like a compound camera just from that. Anyway, so I think that, first of all, it was really cool. And they actually discovered a couple of dwarf galaxies that don't seem to have any dark matter. I think this is it still needs independent verification because there are a couple of teams that have tried this, and some folks have argued that the statistics used are by the original team when they claimed that there was no dark matter. There are some statistical arguments that this is not the case. I think it actually is. I think they have detected they're basically detecting galaxies that are undergoing weird things. Like there's actually a paper literally out yesterday or today arguing that one of these galaxies has actually just been tidally interacting. And so that ended up stripping away a lot of its dark matter. And so I think that's actually what they're observing is real, and it's mostly due to weird effects like tidal interactions with other galaxies.
And the significance of spotting galaxies with no dark matter is it's almost proof there is dark matter, because there are alternative theories for what might be dark matter, like modified Newtonian gravity and things like that, that can't explain this kind of situation.
Yes. So one of the ways that we detect dark matter, just for folks who maybe are not as familiar with this, one of the ways we detect dark matter is by looking at the motions of stars and gas in the visible matter in galaxies. And we see that a lot of the stars and gas rotate faster than we would expect if it was just stars and gas. And so this is where the idea of dark matter came in, because if you add more matter that we just can't see, then you can make the stars and gas rotate faster. But there are other alternative theories. So some people think that maybe gravity works different on large scales or on the scales of galaxies. And that might be causing these weird issues with rotation in some of these galaxies. But yeah, I do think that, I think it's still the case that you can still explain these galaxies without dark matter using, yeah, exactly like you said, like using explanations that still use dark matter. Yeah. No, I think it's a great question. It's very timely. There was literally a paper that came out on this today. So I actually had a nice time chatting about it earlier with some of my friends. So very timely. Yeah. Cool. So I think that's it for questions. Are there any other questions? Feel free to unmute too if you don't want to post in the chat. All right. So we have a question. Do we have any idea how quarks and dark matter affect galaxies? So dark matter, as I said, can act to make galaxies spin up faster. Mostly dark matter just interacts gravitationally. So we think dark matter had a really important role early on when galaxies formed, because dark matter would basically some of the dark matter would clump together and form what we call dark matter halos. And then they would the dark matter halos would gravitationally attract gas and other, what we call baryonic matter, regular matter. And as the gas fell in, it would actually form galaxies. So dark matter does have an effect on galaxies that way. Quarks are just subatomic particles that we think make up regular matter. So we think quarks make up things like protons and neutrons, which make up regular matter. So those don't really affect galaxies, other than everything is sort of made up of protons and neutrons. Cool. All right, I think that's all the questions right now. There's a career-related question. Yeah, I'm happy to answer that now. I can also wait until the end of the talk. It's up to you. Okay, so I think we'll wait on that one. All right, thanks, Anton. Okay, so in the last section of this talk, so far we've mostly been talking about sort of the science behind like why we would want to study dwarf galaxies and cosmic voids. And I hope I've mostly convinced you that they're interesting and that there are reasons to study these systems. But now let's talk a little more about the logistics. So not just the scientific question, but how we actually answer that scientific question, how we actually study the dwarf galaxies in these cosmic voids. And the way we do this is by measuring galaxy properties. So there are a lot of different properties that you can measure from galaxies. You can measure, we already talked about some of them. We talked about the galaxy shapes, we've talked about their sizes. You can measure things like how fast they're forming stars. There are all these different ways to describe galaxies. But in particular, we're going to focus on the chemical composition of a galaxy. And that's because it tells us a lot about how the galaxy has evolved over time, which is the thing that we're interested in. So if we go back to this picture of what galaxies are made up of, and if we just focus on the stars and the gas, again, because dark matter is important, but it doesn't interact as much with the stars and the gas. And so we'll really just focus on these two components. So throughout a galaxy's lifetime, the galaxy is forming stars out of the gas. So the gas turns into stars, and as the stars live, they make heavy elements. And that's exactly what the sun is doing right now. The sun is fusing hydrogen into helium, and that produces all of the energy that we get as sunlight, all the energy from the sun that we need to survive. And stars more massive than the sun can make heavier elements too. So they can fuse, helium into beryllium, into carbon and nitrogen and oxygen, into silicon, all the way up to iron. And so when the stars die, then they release all of those heavy elements back into the galaxy. And the cycle happens over and over again. More and more heavy elements get released as the cycle happens, as the stars live and they die. And so overall, the amount of heavy elements in a galaxy sort of tells you how many times the cycle has happened. And it can also tell you about other things too, like if the cycle was broken, if for some reason gas got removed from the galaxy or gas got added to the galaxy. And so the chemical composition really tells us about how it's evolved over time. And so to measure the chemical composition of these galaxies, we want to look at the colors of light. This is, because until quite recently, most astronomy was done with just light. And so it's kind of amazing how much information we can just get from the light. But if we take white light and we split it up into all its different colors, it's not really white, right? We see a rainbow if we use like a prism or a grating to split up the light. And it turns out that if you do this, if you pass the light through different elements and then you split up the light into different colors, different chemical elements leave fingerprints in light. So hydrogen, for instance, if you pass a white light through hydrogen gas, it'll actually produce what we call these spectral lines, these emission lines at specific wavelengths. And different elements will produce different patterns. And that's because these spectral lines, as many of you might already know, these spectral lines come from electronic transitions in the atoms. So a hydrogen atom, for instance, has one electron, and it has certain energy levels. And as the electron moves between these energy levels, it produces different photons, it produces light at specific colors. And sodium has more electrons than hydrogen, and also different wavelengths, so it'll produce a different pattern. And so these are really sort of fingerprints of each of the different chemical elements. And so what we want to do is take the light from a galaxy and split it up into all its different colors, and then match the light from this galaxy to these different fingerprints. So here's an example of how this works. So this is just a galaxy spectrum, which just records how much light is at each color. And here, the colors we've now numbered them according to wavelength, because wavelength is really just a number that describes the color of light. And so you can see here, you can see here that this red feature, this red bump in the galaxy spectrum is actually from hydrogen. It's produced by hydrogen, and it matches this red line here. And so by matching the different spectral lines we see in a galaxy spectrum to the different chemical fingerprints that we expect, we can measure how much of different elements are in a galaxy. And that will tell us about how the galaxy has evolved over time. So how do we actually get these spectra? So there are a couple ways to do this. Traditionally, spectrographs take the light from just a small part of the galaxy. So in this case, a slit, it's usually either a slit or maybe a small circular fiber, a circular hole at the center of a galaxy. And they take that light and they split the light into all of its different colors. The problem with that is that you're missing a lot of information when you do that, because you're only looking at a small part of the galaxy. You're missing what's happening in all of the outer skirts of the galaxy. And so if you want more spatial information about the full extent of the galaxy and what's happening, you can use cameras. And so this is what the great images that folks took earlier are perfect examples of this. So cameras, you get a beautiful image, you get a lot of the spatial information, but you have to use different filters and you only get a few colors. So if, for instance, you take a picture with your cell phone camera, your phone is really only recording colors in blue, green, and red, and no other colors. And then it stacks those on top of each other, and our eyes perceive those as many colors. But unfortunately, if we want this full information from a galaxy about all these different colors, 3 colors is not going to cut it. And so a camera, you actually lose a lot of information about the spectral information. You lose a lot of, if you want to study chemical compositions, you can't get that information from a camera. And so what we really want is sort of a cross between spectra and images. And that's something, this is a pretty new technique called integral field spectroscopy, which is basically a cross between these two things. It lets us get the best of both worlds. So it's sort of like a camera, except at every single pixel, you get a full spectrum. So you get both the spatial information and you get the spectral information. And one of the best integral field spectrographs or integral field units in the world was actually designed and commissioned by folks at Caltech, and it's called the Keck Cosmic Web Imager. And you might not be able to guess what it was designed to do. It was designed to image the cosmic web. So going back to our picture of the cosmic web and looking at the gas density side, it was really the Keck Cosmic Web Imager, KCWI for short, was really designed to look at all of the areas around where the galaxies live. So they're the bright parts where the galaxies live and where most of the dense gas is collected. But the Cosmic Web Imager was designed to look at some of these fainter filaments. And so I think it's actually really cool to get to use this instrument to not just look at the cosmic web, but actually look at the stuff in between the cosmic web, in the voids. And that's exactly what hopefully half of my thesis will be. I'm going to try to use this instrument to look at dwarf galaxies both inside and outside the cosmic voids and then compare them. And we can start to ask questions like, how many heavy elements are in these two different types of dwarf galaxies? You know, are there more heavy elements in the ones that have been interacting more? That's sort of what we would expect. We expect the dwarf galaxies that are in filaments to have had more interactions and be able to build up more heavy elements. And also because we're using this integral field spectroscopy technique, we don't just get information about the total amount of heavy elements, but we also get information about where in the galaxy those different elements are located. So we can start asking questions like, are there more heavy elements at the centers of galaxies or at the outskirts? And then what does that tell us about how galaxies evolve? We can ask questions about where the stars and gas in a galaxy are located and how they're moving around. And so all of these questions are things that hopefully I'll be able to answer soon. So all of this is coming soon. We have the data and are starting to understand it now. And so to recap, to summarize, the goal is to understand the chemical composition of dwarf galaxies located in cosmic voids and then try to use those to answer questions about galaxy evolution. So hopefully that wasn't too much. I think one of the best things about this whole project is that the story is still ongoing, right? We have the data, we've started reducing and analyzing it, and it's very likely that we'll find something unexpected or that our questions, the kind of questions that we want to answer, will change over time. And so I'm really excited about it. If you're interested in learning more, I'm happy to answer questions now. You can also, I do have a Twitter account and a website, and I post about science there pretty frequently. So if you're interested in following and seeing how the story's going, feel free to join. Thanks so much, everyone. And it looks like we have a few more questions, so I'm happy to start answering some of those. All right, we have a couple questions. So I guess the easiest one is from Dennis. Why am I in Raleigh right now? So I have in Pasadena, I have a tiny studio apartment. And when lockdown started happening and I started being unable to interact with other people, it kind of became a little much. So I went back to Raleigh to stay with my family. And I also managed to get away from, the fires and earthquakes and various other things. So it's a temporary thing. I will probably go back to Pasadena and finish my degree. And I'm mostly just working from home now. All right, and then we have a couple of science questions. So why don't local Milky Way stars interact with the measurements that we're trying to take? I think that's a really great question. Thanks, Jim. So they definitely do. One of the things that we can do is by looking out of the disk of the galaxy. So here's the Milky Way disk, we're in the disk. If we look out of the Milky Way galaxy, we run a much lower risk of running into stars and gas. And so we typically pick targets to look at that are outside of the galaxy disk. The other thing we can do is we sometimes have to do a lot of data reduction techniques to just subtract out stars or avoid stars or mask them out when we're doing our analysis. For most of my galaxies, it's not an issue because they're pretty far out of the disk of the galaxy. But for other, for other galaxies, for other people in my group, this has been a real issue. We have a question from Okay, we had one question from Carl about what's actually driving the larger structure. What's creating the cosmic web and voids? Yeah, so the short answer, and this is a really good question. The full answer requires a lot of cosmology that I studied at one point and have completely forgotten at this point. But the sort of big picture, the gist of it is that in the early universe, the universe was mostly homogeneous. It was mostly like completely well mixed, sort of like what's a good example? Like Jello. So sort of the same consistency, same material, same density everywhere. But very early on, we think there were these quantum fluctuations in this sort of Jello, and some of those fluctuations were sort of like, I'm trying to come up with good like food related metaphors because I'm really hungry right now. It's not really working. It's mostly just making me hungry. But the idea is that we had these fluctuations in the early universe, so that some parts of the universe were very slightly more dense than other parts of the universe. And when I say very slightly, I mean very slightly, like on the order of 1 out of, I think, 10,000 parts. So very, very small density fluctuations, maybe smaller than that. I don't remember the exact number. But over time, those fluctuations actually grew as gravity took over. The slightly denser parts became more dense, and they started attracting more and more mass. And then the less dense parts became less dense over time. So you can sort of see that. Hold on, let me pull up that timeline here. So let me find the image that I'm thinking of. Here we go. So you can see sort of early on, it looked a lot more smoother. And then over time, those density fluctuations got bigger and bigger. And so this is still, pretty late in the universe, the redshift of 4. If we went back even further in time, it would look even smoother than that. So does that make sense? It was really set by these very tiny quantum fluctuations in the initial density of the universe. Sorry, it was a long answer for what seems like a pretty simple question, but is very complicated. All right, and then we had a question from Joel about how an integral field spectrograph works. So that's a great question. There's sort of two general designs. The first is if you basically took a bunch of fiber optic cables and put them sort of at made them different pixels, I guess. So again, one way that we take in a traditional spectrograph, one way to take a spectrum is by putting a very small circular fiber aperture, and then splitting that light. And so you can do that except with just a lot of fibers, like all next to each other. And that's one way. The Sloan Digital Sky Survey they started a survey called MANGA, which is called, it stands for Mapping Nearby It's not a great acronym, but they use a spectrograph with an integral field spectrograph with that design. The Keck Cosmic Web Imager is a little different. So if we look at those traditional spectrographs, they take a long slit of the galaxy and then split that into light. And the Keck Cosmic Web Imager has what's called a slicer, which basically slices the galaxy image into a bunch of different slits and then splits each of those slits into light. And so there's a lot of doing the data reduction on it is actually a lot harder than it sounds because there's a lot of weird geometry that ends up going into it, but that's the general idea. All right, and then we have a couple of logistics questions and career-related questions. I'm super happy to answer those too. What kind of coding programs do I use to reduce data and for my research? I almost exclusively use Python. So it's a good place to start learning if you want to learn how to code or learn how to do basic astronomy programs. There are a lot of really good tutorials out there. I really wish I'd learned it earlier, actually. So the other question was about what I studied in undergrad and what my career path was like. So in undergrad, I studied physics and math. I sort of came into college, I'd taken a physics class in high school that I really liked, and I thought it was all going to be like that physics class, where everything is like putting a block on a ramp and then solving for how long it takes the block to fall down or whatever. And I kind of liked that. I liked they were kind of like puzzles. And so I thought all of physics was going to be like that. So I went into undergrad thinking, yeah, I'm gonna study physics and math. And the more I got into it, the more I realized that physics is a lot more than just blocks on ramps. And also I really liked astro in particular. So I tried a couple of different research experiences. So I think if there are any undergrads in this audience, I think it's a really great idea to see if you can get involved with research, or even high school students, because one, it's good to know if you like research or not, in case you do like it and you want to end up, doing research for a living. It's good to know that. And two, I tried a lot of different research projects. I worked in like a lab for a while, like a soft matter lab. And then I realized that I broke everything that I touched and that no one should ever let me into a lab. I worked on supernova, like supercomputer simulations, and I realized I didn't really like coding for the sake of coding very much. And then I worked at CERN actually for a little bit doing particle physics, which was cool, but I didn't really, it wasn't quite my thing for a couple of reasons. And then I tried astronomy, and I just thought it was super cool. I thought galaxies were cool. I thought space was cool. And I liked the idea of using real data. So, and like actually taking information about the universe and then trying to understand what was happening. So and then I didn't decide until very late in undergrad that I wanted to go to astronomy grad school. So I think it was literally like the summer before I was supposed to apply, I realized, oh crap, if I want to apply, I gotta start, putting things together now. Yeah, and that's how it ended. And then I ended up at Caltech. And to tie this back to the coding thing, I really wish I learned how to program earlier. I did not learn until, again, pretty late in undergrad. So kind of wish I had started earlier. And then what do my parents think? So my dad is an engineer, so he thinks that astronomy is cool, but a little useless compared to engineering. He does like wastewater treatment type stuff. And then my mom actually does computer science. So I sometimes go to her for coding help when I need it. Cool. And then I've gotten a couple of questions about, do I look at low mass galaxies at high redshift? No, I mostly focus on nearby galaxies. Because dwarf galaxies are so faint, at high redshift, the further away from Earth you go, the harder and harder they are to observe, because they're just so faint. And so I tend to study mostly the nearby universe. There are a bunch of questions from Aziz. Do low mass galaxies produce radio signals? Yes, sometimes. Most radio signals in any galaxy come from things that stars are doing in the galaxy. So, and the gas. So there are a couple of different types of measurements you can make. You can measure the gas using certain radio frequencies. You can measure gas masses. And so dwarf galaxies, this is a pretty common thing that folks do, is they try to measure the amount of hydrogen, both atomic and molecular hydrogen, because both of those will produce different radio signals. And then if stars go supernova, for instance, or if there's a lot of star formation in a galaxy, it'll also produce a lot of radio light. And so that's all galaxies to some extent can produce some radio light like that. Let's see, a couple more questions about low mass galaxies. Do they contain black holes? Probably, yes. We think that, so for context, there are a couple of different kinds of black holes. There are sort of the stellar mass black holes, which happen when a massive star dies. And then there are the supermassive black holes. So the ones like the great images that Steve showed earlier from the Event Horizon Telescope, those are the supermassive black holes that are on the order of millions of times the mass of the sun. And those live at the center of galaxies. And so we know that massive galaxies have supermassive black holes at their center. We know that the Milky Way, that's what the Nobel Prize was for this year, was the discovery that there's a compact object, which is probably a supermassive black hole, at the center of the Milky Way. And one ongoing question is whether or not low mass dwarf galaxies also have those supermassive black holes. And there have been a lot of, I think, really tantalizing hints that they do have these supermassive black holes. I think the problem is that since we can't measure black holes directly, so the Nobel Prize was mostly won for observing the motions of stars around the black hole. Unfortunately, in galaxies outside of the Milky Way, we can't observe individual stars because the entire galaxy sort of just looks like a blob. We can't really pick out the motions of individual stars. And so we sort of indirectly observe the black hole by looking at the hot spots of the, so as the black hole is sort of eating matter, accreting matter, it produces this really hot disk of matter, of gas and plasma. And so that can radiate in different wavelengths of light. And so one way to look for these black holes is by looking for the signatures of these accretion disks. And so some folks have started doing that, and it's pretty convincing, actually. I think it certainly seems the case that many of these low mass dwarf galaxies have these supermassive black holes. The question now is how massive do you have to be? Like, what's the limit? Once you get below a certain mass, do you still get these black holes? So we're trying to find that cutoff point, but there's definitely some indications that relatively small galaxies do have these kinds of black holes. And there was one final question. Sorry, I'm receiving a lot of these over private message, so I realize not everyone can actually see them. There was one question about, do Magellanic Clouds, are there any opportunities for the kind of work that I do there? A lot of folks sort of in tangentially related research areas do look at the Magellanic Clouds. So the large and small Magellanic Clouds are the two closest galaxies to the Milky Way. And they're sort of actively falling into the Milky Way now. And so I think they're interesting in a couple ways. They're not particularly interesting for what I'm doing, because again, I'm looking at sort of dwarf galaxies that are in complete isolation. And so the Magellanic Clouds are not really isolated at all. So not for this particular project, but they are very interesting. There are a number of other things that can be done by studying these two galaxies. And on a side note, I don't super like the name Magellanic Cloud. I know that's what everyone calls them, like even astronomers. But so they're named after Ferdinand Magellan, who my family's from the Philippines. And so Magellan was actually killed in the Philippines by the native people because he was kind of a jerk. So I'm personally, not a huge fan of the name. And so maybe that's why I've been avoiding studying them. All right, well, thanks so much for all these questions. I think that's most of them. If I missed yours, I'm so sorry. Feel free to, email me or message me after, and I'm happy to answer more questions. But thanks, everyone. I really appreciate you, coming out on a Wednesday night, coming out to your laptops on a Wednesday night and watching this.
Well, thank you, Mia.
Thanks for staying up late because you're on a different time zone.
Yeah.
That's okay. I'm on the astronomer sleep schedule anyway, so it's not too late.
So I want to thank you very much from all of our members of our organization, even those that have just quietly listened and enjoyed your talk, that it was exciting and interesting. And I think it's a wonderful opportunity for us to see some of the new young astronomers that are out there who will be watching their papers and their YouTube channels where they talk about their work in the future. So, so on behalf of the San Diego Astronomy Association, thank you very much.
Thank you so much again for having me. And for everyone out there, I also just wanted to add really quickly, a quick plug for Caltech Astronomy's Stargazing lecture series. So the next lecture, I think, is actually by Katie Bauman, who was she was made famous by this Event Horizon telescope discovery. And so she'll be talking about that image of the black hole that Steve showed earlier. So just putting that out there. Look up Caltech on YouTube.
Yes, they have a great channel. You're the first one I poached from that channel. So, but not the last.
Yeah, I gave a very similar version of this talk for that channel also. So if you find that, sorry that I'm giving you basically the exact same thing.
So I can tell you that I curate all of our speakers, and I actually watched your talk. That's how I knew what you were talking about, and that you're a great, interesting speaker that's excited about what she's working on, and that's always infectious when you see that kind of bad choice of words these days, but normally it's a compliment that your enthusiasm, gets into everyone else. They can see that you really enjoy your work. And I think that's really great.
Well, thanks. It's been a real honor. I really appreciate it. And I hope at some point I'll get to visit San Diego in person and maybe attend one of these meetings.
You will be welcome.
So I hope y'all stay safe and for being careful in these weird times.
All right. Any last questions before Mia nods off to sleep? No? Okay. So the end of the October meeting of the San Diego Astronomy Association has now occurred. Thank you.